Hello everyone, welcome back to the Revisions Chemistry Review series. In this video, we are going to talk about gas laws. So, kinetic molecular theory is a theory that gives us information about the behavior of gases. And there are four postulates of the kinetic molecular theory. The first postulate says that all of the gases are made of particles that are in continuous random straight line motion. So all of the gases always have, like, they're always moving and their motion is straight line, and it's very random because when they collide with something, then they just change their direction and move continue moving in a different direction. The second postulate says that when particles collide with something, either with each other or the walls of the container, then they transfer the energy between the particles. But the total energy remains constant. This type of collision, where the energy is transferred but the total energy still remains constant, is called an elastic collision. So gas particles always have elastic collisions, according to kinetic molecular theory. The third postulate of this theory says that the volume of gas particles is so small that it's negligible, meaning we can just ignore the volume of the gas particles and we can just say that they have no volume. And the reason that kinetic molecular theory gave for that postulate is that gases have so much space between their particles that it's very hard to say that they have any volume at all. And then the fourth postulate says that because, once again, the gas particles are so far away from each other, their intermolecular forces are so weak that they are negligible. So we can just say that gases have no intermolecular forces, according to this theory. So the problem with kinetic molecular theory is that it explains the behavior of something that can be referred to as the ideal gases. So all of these four postulates that this theory gives us is something that can be true for the ideal gases. But the problem is, in real world, we have real gases, and they do deviate from some of these postulates, especially postulate number 3 and 4. Because according to these four postulates, gases have no volume and they have no intermolecular forces. However, what if you apply pressure on the gas particles and you bring those particles closer together? In that case, we can say that they're going to occupy some volume and they're going to have some intermolecular forces. So, postulate 3 and 4 might not be that true after all, especially for the real gases. So, if you have to compare the ideal gases with the real gases, ideal gases normally occur because, remember, we want the ideal gases to have absolutely no volume and absolutely no forces of attraction, no intermolecular forces. So that is only possible when we have very, very low pressure, because at very low pressure, the particles are super far away from each other. So they are going to have no attractions between the particles, and they are going to have kind of negligible volume. And also when we have very, very high temperature. So at high temperature, the particles are moving so fast that they are once again going to have no attractions, and it's going to be very hard to confine them into one place. So here's kind of the explanation of those two things. So this is a super important thing to remember. There's like a very high chance that you're going to get one question on this, that in order for any gas to behave as an ideal gas, what conditions are necessary. So remember that ideal gases exist at very low pressure and very high temperature, because at these two conditions, it's very hard to have any volume and it's very hard to have any intermolecular forces. Real gases, however, exist under high pressure, because if you have very high pressure, the particles are getting closer to each other, so they are going to have some sort of volume and intermolecular forces. And if you have very, very low temperature and the particles are moving very slow, now there is a chance that they're going to have some sort of attractions between them. So another type of question that you might get is which gases are more likely to behave as an ideal gas. So those are normally the gases that are very, very small, because for bigger gases, it's hard to not have any volume or to not have any intermolecular forces. So gases like hydrogen and helium are more likely to behave as ideal gases. So let's talk about some gas laws, meaning if we change some of the conditions for the gases, how are the other conditions going to relate to each other? So Boyle's law said that if we have constant temperature, then the volume and the pressure of the gas are going to be inversely related to each other, which means if we increase one thing, the other thing is going to decrease. So here's kind of like a representation of that. So we are saying that if we have very high volume, that means there's a lot of space between the particles. To make that possible, we need to have very low pressure, because if you have low pressure, that means we're going to have a lot of space. But if we increase the pressure, the space is going to be less. So that is an indirect relationship between volume and pressure. So sometimes you might be asked that if you double the pressure, what happens to the volume? So remember that they are proportional, so you kind of have to take into account the proportions. So if you're doubling the pressure, volume is going to be 1/2. If you are increasing the pressure 3 times, volume is going to decrease 3 times. So it's going to be 1/3 of what we started with. Here is what the graph of your pressure versus volume is going to look like. So now notice that this graph is not a straight line. So it does not look like this. And that's because if you make your graph like a straight line, eventually what's going to happen is that it's going to give us a volume of 0. And that is not possible. Volume can never be 0. So the volume for the pressure versus volume graph is an exponential function, because we want to make sure that the volume is never equal to 0, because it cannot be. So using this graph, if let's say we pick any 2 points on this graph and we try to write an equation for Boyle's law, it turns out to be P1V1 equals P2V2, where P1 is your initial pressure, V1 is initial volume, P2 is final pressure, and V2 is the final volume. Okay. Let's look at Charles' law. So this law states that at constant pressure, the volume and temperature are directly related, meaning if you increase the volume, temperature is also going to increase. So let's think about this liquid nitrogen example. So if we take inflated balloons and we put them in liquid nitrogen that has a very, very low temperature, so the volume of the balloon is also going to decrease. However, when we take them out of the liquid nitrogen, now the temperature surrounding the balloon is going to increase, so the temperature of the gas inside the balloon is also going to increase, so the volume is going to increase as well. So if you are asked to say that what if we double the temperature, what happens to the volume, and so on and so forth, remember to take care of the proportions. So if you double the temperature, volume also doubles. If we increase the temperature 3 times, temperature also increases 3 times, and stuff like that. The very important thing to remember about Charles' law is that your temperature must be in Kelvin, and that's because for other scales of temperature, like for Celsius and degrees Fahrenheit, we can have negative temperatures. However, for gas laws, when we look at the equation, you'll notice that temperature is in the denominator. So it must not be negative, because if it's a negative number, it's going to give us weird numbers for our calculations. So we always want a positive number for our calculation, and the only scale that can give us a positive number is Kelvin. There is no negative Kelvin temperature. The lowest possible temperature for Kelvin is 0 Kelvin, which is also it's never achieved in the world as of this moment. It's called an absolute 0, just like we talked about in class. So this is what your graph for volume versus temperature is going to look like. It's a direct relationship, a linear relationship. The equation is going to be V1 over T1 equals V2 over T2. So V1 and V2 are your initial and final volumes. T1 and T2 are your initial and final temperatures. Remember, they have to be in Kelvin. The Guinness Law is when you keep your volume and number of moles constant, and then pressure and temperature are going to be directly related. So think about this example over here. When you have a lower temperature, that means particles have very low average kinetic energy. So in that case, pressure inside the container is also going to be lower. But if you increase the temperature, now the particles are moving very fast, so that is going to increase the pressure of the gas particles. So keep your proportions under account. Doubling the pressure is going to double the temperature. Increasing your pressure by 3 times is going to increase your temperature by 3 times. Your graph is going to be a linear function going up. Remember that you want your temperature to be in Kelvin, and your equation is going to be P1 over T1 equals P2 over T2. Let's talk about the combined gas law, which is when we combine these 3 laws that we just talked about. So it's the combination of Bose, Charles, and Gay-Lussac's law. The equation is P1 over T1 equals P2 over T2. It is given in table T. And by the way, because this equation is given in table T, you kind of don't necessarily need to remember the exact equations for the other laws, because if your question is telling you that you have constant temperature, that means you can just ignore the temperature and your equation turns out to be P1 or V1 equals P2 V2. If the question tells you that your volume is constant, you can ignore the volume and your equation turns out to be P1 over T1 equals P2 over T2. If the question tells you that your pressure is constant, you can ignore the pressure and the equation turns out to be V1 over T1 equals V2 over T2. Okay, so you can use the combined gas law to kind of derive the other laws that we have talked about. So let's talk about the last gas law, which is the Avogadros Law. So Avogadros Law tells us that if we have equal volumes of different gases at STP, this is kind of the key word, if we have them at STP, then you're going to have the same number of moles and same number of molecules. What we mean by that is, let's say we have these 2 completely different gases, but we have them at the same pressure and same temperature. So we have them at 2 atmosphere and 273 Kelvin. So because these conditions are the same for both of them, that means they're going to have same number of moles and same volume. So they're going to have 6.02 times 10 to the power of 23 molecules if they have 1 mole, and they are going to have 22.4 liters again if they have 1 mole. But if they have like something like 0.5 moles, then the volume and the number of molecules are also going to be 1/2. So let's look at this example over here. We have these 3 gases. We notice that their pressure and temperature is the same. They all have 1 mole, so their volume is also going to be the same. The equation that we use for Avogadros law is V1 over N1 equals V2 over N2. This one is not given anywhere, so you're going to have to memorize this one. So remember that P1 and P2 are the initial and final pressures, N1 and N2 are the initial number of moles, or the number of moles of gas 1 and the number of moles of gas number 2. So let's do some calculations using these gas laws. Here is the first equation. So we have a gas that occupies 12.3 liters at a pressure of 40 millimeter of mercury. What is the volume? And the pressure is increased to 60 millimeters of mercury. So we notice that we have 12.3 liters. That's your initial volume. And we have initial pressure of 40.0 millimeters of mercury. It's asking for the final volume. So the V2 is missing. And then we have 60 millimeters of mercury at the final pressure. So we are looking at the relationship between pressure and volume. So that's going to be your Bose law. And the equation for Bose law is P1 V1 equals P2 V2. If you are looking for the V2 from this equation, we can go ahead and divide both sides by P2. So it gets cancelled here. And your equation is going to be P2 equals P1 V1 over P2. So you can just go ahead and plug in your numbers and get your answer. So here's another example. Calculate the decrease in temperature when 2 liters at 20 degrees Celsius is compressed to 1 liter. So 2 liters is your initial volume, 20 degrees Celsius is your initial temperature, and 1 liter is your initial volume. Final volume. So it's asking to find the final temperature. So That means we are looking at the relationship between volume and temperature, which is going to be your Charles law. And we are looking for the final temperature. So if you want to rearrange this equation, the first thing that we can do is cross multiply these two numbers. So we end up with V1 T2 equals V2 T1. So now if you want to isolate the T2, we can go ahead and divide V1 on both sides. So that gives us this equation, T2 equals V2 T1 over V1. One more thing to take care of here before you plug in the numbers is that your temperature must be in Kelvin. So make sure that you do 20 plus 273 and you get 293 Kelvin. So don't plug 20 degrees Celsius in your calculation. Make sure you plug 293 Kelvin so that your answer is also in Kelvin. Here's another example. We have a sample of neon gas that occupies 4.61 liters at 2.83 atmosphere and 277 Kelvin. What will be the pressure of the gas in atmosphere when 8.3 liters are occupied at 293 Kelvin? So here we have the initial volume, we have the initial pressure, and we have the initial temperature. And then they give you the final volume and the final temperature, and they're asking you for the final pressure. So because all three quantities are changing in this case, that means we're going to look at the combined gas law, and we are looking for the final pressure. So let's rearrange this equation. We can go ahead and multiply T2 on both sides. So that is going to cross out the T2 here. And then for the V2, we can go ahead and divide V2 on both sides. So that is going to cancel out the V2 here. So our equation is going to be P1 V1 T2 over V2 T1. So once again, in this case, you actually don't have to convert your temperatures to Kelvin because they're already given in Kelvin. So that's one less step. So just plug in the numbers and calculate your answer. All right, finally, how many moles of gas were present in a 67.2 liter sample if only 11.2 liters of the sample is left now? So 67.2 liters is your initial volume, and then 11.2 liters is your final volume. And then it's saying how many moles were present initially if we only have this many moles left now. So we're going to use Avogadros Law in this case. And so remember that the equation for Avogadros Law is V1 over N1 equals V2 over N2. So if we are looking for initial number of moles, we're going to have to kind of do cross multiplication. So we get V1 N2 equals N1 V2. So once again, if you want to isolate the initial number of moles, we're going to divide both sides by V2. So that gives us N1 equals V1 N2 over V2. Now let me plug in the numbers here for you. So the initial volume is given as 67.2 liters and the final volume, the final volume is given as 11.2 liters. What is not given to you in the question is the final number of moles. However, we can calculate the final number of moles because remember, according to Avogadros Law, 1 mole of any substance at STP has 22.4 liters, right? So if we have 11.2 liters, that means we have 0.5 moles. So 0.5 moles is going to be equal to 11.2 liters. So that means our final number of moles is 0.5. Alrighty, so this is how we work with the gas law problems. So that was the end of this unit. I will see you in the next one.